All right, let's talk about a set of conditions called standard state. Now, this is pseudo-ish STP. Standard state here is a set of conditions for which everything else is compared. And we're doing it such that the pressure is 1 atm. We could also do 1 bar, or concentrations of solutions are at 1 molar. We're always using it for pure stuff. And this is going to be a comparison point. So we're picking standard state. Now note there's no temperature involved. We're going to tend to measure it at 25 degrees Celsius, but seriously, standard state, 1 atm and 1 molar. When we talk about standard state, so if we're looking at our delta H, our change in enthalpy, change in heat at constant pressure, the little zero means standard state conditions. We could take and tabulate these at any temperature, but we tend to do it at room temperature, and we do it at 298 Kelvin. And so when you look at your charts of standard molar enthalpies, they will be tabulated or listed as a certain temperature, and the ones in the book are at 298 Kelvin. Now, we frequently normalize this. How much heat is going to be involved depends on how much we have. So to get rid of the variability on that, we normalize it by dividing it by moles. So our delta H, standard state, is going to be the heat at constant pressure divided by the number of moles involved, and this is going to be tabulated in units of kilojoules per mole. All right, we can look at or calculate standard enthalpies of multiple reactions, and one of which is combustion. We frequently call it heat of combustion. And this occurs when 1 mole of whatever substance we have burns with oxygen, however many moles of oxygen it needs under standard state conditions, means at 1 atm. For example, the standard enthalpy of combustion, meaning 1 mole of ethanol burning with oxygen here, making carbon dioxide and water. Standard state here at 25 degrees Celsius means we're going to have water as a liquid. And our enthalpy for this, or heat released, is minus 1366.8 kilojoules. This would be for 1 mole of ethanol reacting with 3 moles of oxygen. So this would be minus 1366.8 kilojoules for either 1 mole of ethanol or for 3 moles of oxygen, etc. Now, more importantly, it's standard enthalpy of formation. Now, why? Because this is how we tabulate our heats, and we're going to use our heats a lot for our reactions. So standard enthalpy of formation is to synthesize or to make something from its elements in their most stable form at 1 atm. So if we were going to make carbon dioxide, its elements are going to be carbon. Now note there's multiple forms of carbon, but the most stable form happens to be graphite. So we'd have 1 mole of graphite. We need an O2. That's going to give us 1 mole of oxygen, and it's going to react to make 1 mole of carbon dioxide. Now, we define the enthalpies of formation of the elements. So delta H, not a formation, the most stable form of the elements. We define these to be 0 just to make our lives easier. And when we compare the enthalpy of the products here to our elements, this is going to be how much heat is released or formed or absorbed as this reaction occurs. So it's going to be to make 1 mole of a compound from its elements, where the delta H, not a formation of the elements, is 0. So we need to be able to write these equations. So if we're going to make ethanol, C2H5OH, we have to realize which elements are involved. Now, if you're not sure which elements are involved, go to your appendix, and I think this is Appendix G, and find the element that has a delta H not formation equal to 0, because that's going to be what we're going to make it with. So, for example, our carbon is listed as C, our hydrogen is listed as H2 as a gas. Those are the 0 forms. And our oxygen is O2 as a gas. And we're going to make ethanol as a liquid. Now we have to have the right amount. Well, if we got 2 carbons here, we need 2 here. If we add our hydrogens, we get 6 atoms of hydrogen over here, which is going to be 6 moles of H2. Now we can have fractions in these reactions, and sometimes we have to, because we only have 1 atom of oxygen over here, which is going to give us a 1/2 here. Now, if we're going to make instead calcium phosphate, Ca3PO4 2 as a solid. This is going to be made up of calcium, phosphorus, and oxygen. Now, phosphorus does not exist as P itself, it exists as P4. If you weren't sure, you really would go to your charts and figure out the one that has an enthalpy of formation of 0. Now we balance it. We have 3 calciums, which exists as a solid. We're going to have 1/2 of a P4 as a solid, and we're going to have 4 moles of O2 as a gas. And those are the reactions, delta H naught, of formation of these products. Now, if we want to know how much heat is involved in a chemical reaction, we can do it 2 ways. 1, we can go to the lab and measure it experimentally. Or 2, pretty much, we could go to our charts or we can cheat. So step 1, we're going to cheat, and we're going to do and use HESS'S law. HESS'S law says that the enthalpy change of a reaction, total process, can be written as the sum of sequence reactions, and the enthalpy of the overall process is the sum of the enthalpies of the sequence reactions. What does this mean? This means if we have some reaction with an enthalpy, and we have another reaction, and we have its enthalpy, if we can use these reactions as like puzzle pieces to get the enthalpies that we need, we can get the enthalpy for the overall reaction. And we can do this because enthalpy is a state function. It doesn't matter how we get to the end process, only that we physically get there. So it only depends on where the process starts and where it ends up, and not the path that it takes in order for it to finish. So let's think about this. For example, if we want to make carbon dioxide, we can look up the enthalpy of formation of carbon dioxide, and we can take carbon and react it with oxygen to make CO2, and that is a direct process. But there's other ways of doing this that would be indirect that would still give us the same value. So let's imagine that we're going to do a 2-step process, that we take carbon as a solid and react with 1/2 of a mole of oxygen to make CO. And then we take that CO and react with another 1/2 of a mole of oxygen to make CO2. And we have 2 enthalpies. Now let's add these up, because HESS'S law says that the enthalpy, delta H, for the overall reaction is the sum of the enthalpies, our delta H's, for the sequence reactions. So our sequence reactions are these 2. So if we take and we add these up, we have 1 carbon here, 1/2 of an oxygen, and another 1/2 of an oxygen. We add a CO here, and so what we have here is a carbon, 1 mole of oxygen, and a CO. On our product side, we have a CO and a CO2. Well, if we look at these, we have a CO on the reactant side and a CO on the products, which means that carbon monoxide is really a spectator, and we're just going to cross it off. If we sum up our oxygens, we're going to have, instead of 2 1/2 of an oxygens, we're going to have 2 of those, and we're going to have 1 O2. When we add these up, we get carbon as a solid plus oxygen as a gas makes CO2 as a gas. Well, HESS'S law says that as long as our reaction, when we add them up, gives us what we need, we can add up our enthalpies. And when we do this, our delta H for the overall reaction is going to equal minus 111 plus a minus 283, which is going to be minus 394 kilojoules, which is right about what we need. So, HESS'S law. In a graphical form, we can see that if we take carbon and oxygen and we go directly for CO2, we get this value. If we go indirectly through carbon monoxide and oxygen, we are still going to get the same value. That is the fundamental process of HESS'S law. Now we're going to use this for other types of reactions, but let's do an example first. So we want the standard enthalpy of formation of carbon disulfide given some pieces. Now, my advice is when you do these is to number these so you can keep track of them. And what we want is the formation of CS2. Well, the formation of CS2 means we take carbon disulfide, we'd make it as a liquid, we'd make it from its pieces, which is carbon as a solid. We'd go to our chart and realize that sulfur exists most stable as a certain type of crystal called rhombic. To get 2 over here, we need 2 of our sulfurs over here. We're going to assume that they're rhombic and that this is going to be our reaction. So this is what we want. And these are the pieces that we're going to use, our indirect process that we're going to use to get there. Now, the easiest way to do this is to go through and find all the major players in the reaction that you want and put them where you need them, i.e., I need 1 carbon as graphite. So I'm going to take equation 1 as written. Carbon as a solid plus oxygen as a gas goes into CO2 as a gas, and it's going to have an enthalpy of minus 393.5 units of kilojoules. Moles, by the way, do not belong there. Now, second major player. I need sulfurs, and I need 2 of them. Well, if I need sulfurs and I need 2 of them, I'm going to take equation number 2, and I'm going to multiply it by 2, because that's going to give us 2 sulfurs. Now, at some point, you're just going to pray that the rest of it all works out, and conveniently, the people who do this are experts, so it's going to. So 2 sulfurs plus 2 oxygens goes into 2 SO2s, and our delta H for that is going to be 2 times the minus 296.1. All right, that's going to give us our 2 reactants. Now, for a product, we need CS2 here over as a product. And if we look at equation number 3, CS2 is a liquid. Well, we can reverse equations. Well, I'm going to take equation 3 and I'm going to reverse. If I take equation 3 and I reverse it, I'm going to get carbon dioxide as a gas plus 2 SO2s as a gas reacts to make CS2 as a liquid plus 3 O2s as a gas. And the enthalpy for that is going to be reversed. So our delta H is going to be positive 1072. Now, I'm going to take a look and find my spectators. So my advice is to take a look and see what goes in and comes back out. So in this case, I realize I've got carbon dioxide here as a product, carbon dioxide here as a reactant, goes in and comes back out, so it's a spectator. I've got 2 SO2s as a gas here as a reactant, 2 SO2s as a product. I'm going to cross them off. They're not involved in the reaction. Then I'm going to go to my oxygens. Over here, I have 1 on one reaction and 2 on the other for a total of 3 oxygens. Over here, I have 3 oxygens, and so that is going to cross off as well. When I add this entire mess up, I'm only going to be left with carbon as a solid plus 2 sulfurs as a solid goes into CS2 as a liquid. And although there were multiple other indirect steps here, they aren't relevant because they all cross off and I get exactly what I want. Enthalpy is a state function, so I get to do this. And when I finish my math, I'm going to get a delta H for this reaction is equal to 86.3 kilojoules. So what we realize as we're looking at Hess's law is that if we dissect our stepwise reactions, they come up with a pretty consistent thing. And that is that we take our reactants and break them into the elements, and then we take the elements and put them back together to make products. Well, if we do that, we can come up with one final equation. And the final equation is that the enthalpy of a reaction is going to equal the sum of the number of moles of the enthalpies of formation of the products minus the sum times the number of moles of the enthalpy of formation of the reactants. In the sense here, you're going to look at products minus reactants. And when we do this, we can actually prove this using Hess's law, but we can just take and go to our table, find the enthalpies of formation, take final minus initial or products minus reactants, make sure we have the right number of them, and get the overall enthalpy for the reaction. So if we have the reaction of 3 NO2s as a gas plus a water as a liquid, making 2 nitric acids aqueous and an NO as a gas, where are we going to find these? Well, we're going to go to our appendix, and we're going to realize that we have to do products minus reactants, and we have to include how many? So we're going to start out with 2 moles nitric acid. We're going to look up its enthalpy of formation. We're going to add to that 1 mole of NO multiplied by its enthalpy of formation. We are going to subtract 3 moles of NO2 plus 1 mole of water times their enthalpies, and we'll get the overall enthalpy for the reaction. So let's do one more and make sure we can make this work. So if we want the enthalpy of combustion for benzene, where this is going to be our balanced reaction, the first thing we have to do is find our delta H's. So when we go to our table and we find the delta H not a formation, and we're going to do this at 298 Kelvin until we have a compelling reason not to. Our values here for benzene is positive 49.1 units of kilojoules per mole. Oxygen is 0. Carbon dioxide is minus 393.5. And water here as a liquid is minus 285.6. So the delta H for this reaction is going to be the sum of the number of moles. We're going to start out with carbon dioxide, and we're going to have 12 mole of CO2 multiplied by its enthalpy, minus 393.5 kilojoules per mole, plus 6 moles water multiplied by its enthalpy, minus 285.6 kilojoules per mole. And that's going to give us our products. We are going to subtract our reactants, 2 moles benzene multiplied by 49.1 kilojoules per mole, plus 15 moles of oxygen multiplied by 0. Final minus initial, products minus reactants, remembering to get the number of moles. If you finish the math, you're going to get minus 6534 kilojoules.